Hi everyone, in this video we'll look at a function approximating neural network and discuss its purpose, design, and underlying math. I'll play a video of the network training in action. The algorithm starts with randomized parameters. Through training, its goal is to approximate the output given the input of 41 samples. Input samples are values evenly spaced between -1 and 1. The desired output versus input is graphed by the solid blue line, and the network output versus input is graphed with points. Features of the network includes two hidden layers, ReLU and linear activations, L1 and L2 regularization, and atom optimization. Loss is calculated using mean squared error. Here's the shape of the network. Referencing the text neural networks from scratch in Python, two hidden layers seem to work well for this kind of function approximator. A 1 by 3 by 3 by 1 network size seemed to work consistently well across many trials. Now let's get to the math. Let's focus only on the last layer's forward and backward pass, as well as the error function. I think it helps to visualize the matrices and operations to understand what's going on. To make this manageable, I'll use a sample size of 2 instead of 41. First, let's look at the forward pass. We start with the data input to this layer, the X matrix. X is organized as such. Each row corresponds to the sample number, and each column corresponds to the input node number. X is organized differently from parameter terms, their format is as shown. For clarification, the blue 1 in front of the bias matrix indicates that its row size for any input node size is always 1. The first math operation sees a multiplication between X and the weights. Next, bias terms are added. Finally, the linear activation function is applied. One thing to note, the linear activation function's input and output are the same. The final forward pass result is shown in red. Now we move on to error. We take the forward pass output and apply it to the error function. The result of this can be simplified to that del matrix. Calculation of parameter derivatives needed for network training start with derivatives of del, which makes use of the chain rule. What's in purple gets passed to the back end of the last network layer. This starts the backward pass. If we take partial derivatives of the purple values in terms of parameters and layer input X, we get the following derivative matrices. Each element between the derivative and non-derivative counterparts corresponds to one another by position. For general input, output, and sample sizes, here's the linear algebra for forward and backward pass math. We're looking directly at the code here. To update parameters from passes, I'm using atom optimization. This is more involved than simply adding the weight and bias derivatives from the passes to the weights and biases. Atom does two special things. One calculates a moving average of weight and bias derivatives and adds this to weight and bias terms. This is called momentum. It helps the algorithm get out of local minima. 2. Atom gives a boost to derivatives influence on parameter updates who have moving averages near 0 to encourage their accompanying parameters to participate meaningfully in the training. One last note, I've also included the L1 and L2 regularization in this function. This kind of regularization prevents individual parameters from dominating significance by suppressing any parameters that get too high in magnitude relative to others. Full code is on these next two slides. Leave a like if you learned something. Comment if you got a question or a suggestion. Thanks for watching.